Next question. Question number 34. Arrange in the increasing order of reactivity with the nitration mixture. Increasing order of reactivity with the nitration mixture. That means increasing order for the electrophilic substitution reaction, right? You know, towards electrophilic substitution reaction, electron donating group will act as activating group. There are activating groups and deactivating groups, right? Electron donating groups which show plus I effect, which show plus R effect, will be activating group. Normally they are orthopara directing in nature and they are activating in nature. The ring is getting activated and they will show maximum reactivity. And it's very simple to understand, no? You see, this is activating group and this is highly deactivating group and this is slightly deactivating in nature. So this should be most reactive. C should be most reactive and that gives us the answer straight away. Option 3 the correct answer because C maximum varana and that is available only in one choice. Okay. So C maximum. After that, is it A correct? Yes. This is electron donating group. OCH3 is electron donating group and the other two are electron withdrawing group. Presence of electron donating group activates the ring. Okay. Presence of electron withdrawing group deactivates the ring. And I am sure all of you know that NO2 is a powerful deactivating group. So that should be minimum. And chlorine is slightly deactivating. And regarding chlorine, I think all of you remember, chlorine is slightly deactivating. At the same time, it is orthopara directing in nature. Normally, deactivating groups are meta-directing. Chlorine is slightly deactivating and it is orthopara directing. That is another important point. So, methoxy group when comes and that is most reactive and then it is chlorobenzene and then it is nitrobenzene. Okay. Next question. 35. Right. You have a sequence given here. Compound P undergoes following sequence of reaction. P is. Let us verify. Suppose it is cyclohexane carboxylic acid. Cyclohexane carboxylic acid. That is what first option. This is treated with ammonia and heated. First you will get ammonium salt, not benzene. First you get ammonium salt and upon heating it will be converted to amide. You get a cyclohexane amide, right? Amide is obtained and that is Q. Idana Q. Okay. Now that is treated with KOHBr2. I am sure all of you understand what the reaction, the first reaction in the second sequence. It is Hoffman's degradation reaction. Hoffman's degradation reaction. And what is the result of Hoffman's degradation reaction? This group will be out. And the result will be you get a amine. You get a cyclohexyl amine. Right? And when treated with this one, chloroform alkali, a primary amine with the chloroform alkali, that is carbylamine reaction, isn't it? Isocyanide test, carbylamine test, and the result will be the requisite compound we are talking about, and that means the answer is first choice itself. The answer is first choice itself. Answer is first choice itself. A carboxylic acid converted to amide and that amide, Hoffman's degradation reaction, you get amine and finally carbylamine test, chloroform with the alkali. And you see that is not matching with anything else. This is an amide. This is what Q is given in the second choice. And in the third choice, you can see there is one carbon extra. There is one carbon extra. You see, this carbon will be extra. What about the fourth choice? Fourth choice, it is given ketone. Fourth choice, it is given ketone, and that does not substantiate the given reaction. So starting with the cyclohexane carboxylic acid, it is converted to ammonium salt. Upon heating, you get amide, and then Hofmann's degradation reaction, you get amine, and then finally carbylamine test chloroform with the alkali. First choice will be the correct answer. Okay. Next. Question number 36. Some statements are given and one reaction given. But-2-ine and hydrogen 1 mole each separately treated with palladized charcoal and sodium in liquid ammonia. This is Lindlar's catalyst. And you know this reaction, Birch reduction, the so-called Birch reduction. Respectively, getting compound product X and Y respectively. We need to identify the incorrect statements. There are 4 statements given, which is incorrect statement. That is the question. Okay. X and Y are stereoisomers. X and Y are stereoisomers. One of the very important reaction, but-2-ine. But-2-ine, when treated with palladized charcoal and limited amount of hydrogen, you will be getting but-2-ene, which is cis product is obtained. All of you remember, you will get a but-2-ine converted to but-2-ene. Method of preparation of alkyne. The chapter is hydrocarbons. First method of preparation of alkenes. Alkenes in the method of preparation, the first reaction. Alkynes, upon controlled reduction, we get alkenes. And there is a stereochemistry involved. Everybody remember the importance of that 2 reactions given. Lindlar's catalyst, if you are making use of, the given alkyne gives cis product. If the product obtained is capable of showing cis-trans geometrical isomerism. If you make use of Lindlar's catalyst, the product is cis product. And if you make use of sodium in liquid ammonia, the product is trans product. One is syn addition, one is anti-addition. Catalytic hydrogenation is syn addition and chemical reduction is anti-addition. Okay, so here you get a cis product, while the next one here. So here you are getting cis product, while here you will be getting trans product. A very important reaction available in the textbook we are learning. This is cis product and this will give you trans product. So statement 1 is correct answer. Statement 1 is correct. Correct statement. We want incorrect statement. Appo this correct ആണ്. അപ്പോൾ A വരാൻ പാടില്ല. Incorrect ആണ് നമുക്ക് വേണ്ടത്. അപ്പോൾ ഇതും കട്ട് ചെയ്തു, ഇതും കട്ട് ചെയ്തു. Okay, A should not come in the choice. Dipole moment of X is 0. Dipole moment of X is 0. This is wrong statement and it should be a part of our answer. Because dipole moment of this is not 0. You see, this is the cis molecule. This is the cis molecule and you have a definite dipole moment. One moment in this direction, one moment in this direction. There is a moment in this direction. While in trans, the dipole moment is 0. CH3, CH, double bond, CH, CH3. Here the dipole moment is 0. It will be like this. There will be mutual cancellation. Dipole moment will be 0. So X, the product X which is cis, dipole moment 0 alla. While Y which is trans product, dipole moment is 0. So B is a incorrect statement and that should be one of our answer, but we don't get the answer. Now see, boiling point of X is higher than Y. Boiling point of X is higher than Y. That is a correct statement. That is a correct statement because here you have a definite dipole moment. Here you have a non-zero dipole moment. When there is a non-zero dipole moment and here you have a zero dipole moment. So there is a definite polarity. When there is a definite polarity, that add to molecular attraction. When the molecular attraction increases, boiling point increases, right? So boiling point of X higher than Y is a true statement and hence we get our answer. Option 1 should be the answer. കാരണം C ഒരു true statement ആണ്. What about D? X and Y react with ozone, zinc, water to give different products. No, that's a wrong statement. This is a wrong statement and is part of our answer. Why? Whether cis compound or trans compound you take, cis trans configuration does not affect ozonolysis product. Ozonolysis product does not get affected whether you take cis or trans. Whether you take cis or trans, how do you get the ozonolysis product? Is going to break over here and you will get 2 moles of CH3CHO. Whether you take this or whether you take this, you will be getting CH3CHO. CH3CHO. Same as here. CH3CHO. Whether it is cis or trans configuration, that does not affect the ozonolysis product. Ozonolysis product means just to break over that double bond region and you get the corresponding molecule after which getting reduction cleavage. You get aldehyde or ketone, same aldehyde, mixed aldehyde and a ketone. According to the nature of the alkene taken, here it is but2-ene. But2-ene undergoing ozonolysis, you get 2 mole ethanol. 2 mole ethanol, whether it is cis or trans. Okay. So the incorrect statement is option B incorrect, option D incorrect, and hence our answer. Okay. Next question. Question number 37. Once again, a sequence of reaction given. A sequence of reaction given. Let us find out. The product Y formed is. Let us figure out what is the reaction. Here you have given with a gem dibromide treated with the 2 mole NaNH2. So when it is treated with the 2 mole NaNH2, first the bromine goes and hydrogen goes. Here you get a double bond. So this is what the product number 1 after reacting with the 1 mole NaNH2. When again the reaction happens, you can see it turned double bond. So X equal to this is X. That is 2-step dehydrohalogenation. You get X. First NaNH2 react. NaNH2, sodium amide act as a very good dehydrohalogenating alpha beta eliminating agent. Okay. So one of the bromine goes and hydrogen goes, you get like this. Again once more bromine and hydrogen goes, you get like this. This is X. Okay. Now again it react with NaNH2. What is going to happen? It is acidic nature of the hydrogen connected over here. This hydrogen is acidic in nature and that will respond to this, and NH2 minus and H plus will out. You see this NH2 minus and H plus will out as ammonia and you will get a sodium salt. After first reaction, the product obtained will be like this. C minus Na plus. This is the product obtained after that first reaction between X and Y. And now it is interacting with the second reaction. It will undergo a nucleophilic attack. This will attack for a nucleophilic attack and the result is going to be ഇങ്ങനെ വന്നു, ഇവിടെ കാർബൺ and that is interacting like this. This is the product. This is the final product Y. This is the final product Y. And what will be the name? What will be the name of this compound? 1, 2, 3. 1, 2, 3. So for triple bond, both the numbering are same. Here we have a branching, so I am giving from this side 1, 2, 3, 4, 5, 6. So it will be 2-methyl hex 3-ine. 2-methyl hex 3-ine. First option is the correct one. So we have to understand the entire sequence involved in the reaction and get the final product and give the IUPAC name of that molecule. I repeat, here two-step elimination reaction to get a alkyne, ethyne, 1, 2, 3, 4. Butane is obtained. 1 butane is obtained. And that 1 butane, when treated with NaNH2, you get a salt indicating the acidic nature of that particular hydrogen in the terminal carbon. And that undergoing SN attack with this alkyl halide, we get the final result. Okay, next. Again, we have a sequence of reaction to identify which is the final product B. Okay, let's say an aliphatic amine given which is treated with the C6H5COCl. The product will be like this. I mean the compound A. The compound A. It will be NHCO benzene. This unit CH2 NH2 with this benzoylation reaction. Benzoylation reaction. This one hydrogen and this one chlorine will out as HCl, and the net result will be you get a amide. An amine with the acid chloride, you get amide NHCOC6H5. This is compound A. Okay. Now this is reduced with the lithium aluminum hydride. This is reduced with the lithium aluminum hydride. And what is the reduction? Lithium aluminum hydride. This group will be converted to CH2 group. This group will be converted to CH2 group, and the final product B will be, you have cyclohexane ring here, and you have NH here, and this will turn CH2, and this is the molecule. This is the molecule, final molecule. Nothing but this over CO group will be reduced to CH2 group. CO group will be reduced to CH2 group. Option 1 itself is the correct answer. Option 1 itself is the correct answer, and you can see others, why not? Okay. So number 1, it is benzoylation reaction forming amide. An amine with the benzoyl chloride, you get a amide, right? And that amide, when treated for lithium aluminum hydride, CO group will be reduced to CH2 group. You get a amine. Okay. Next. We have a cycloalkene. We have a cycloalkene X on bromination consumes. A cycloalkene X on bromination consumes 1 mole bromine per mole of X and gives the product Y, in which carbon bromine content is 3:1 ratio. The percentage of bromine in the product is, percentage of bromine in the product is, you see, any alkene you take, suppose I am taking cyclopentene, for example, we don't know which alkene we are taking. It is cycloalkene that we know. Cycloalkene that we know. Okay. So just for example telling, Cyclopentene, if it is treated with bromine, you know the reaction in CCl4. It will be bromine added across here and you get a product like this. One bromine here, you get a vicinal dibromide. Vicinal dibromide. Okay, that means for a particular cycloalkane, when treated with the bromine, it is commended 1 mole bromine per mole of X is consumed. 1 mole bromine per mole of X is consumed. That means 1 mole Br2 will be added. That means 2 bromine will be added per mole of the compound. Okay. So what you can understand is, so we don't know what part is this. We don't know what is this. Suppose here there are n carbon. Suppose carbon number is n. We can see bromine number is 1. Suppose there are n carbon, number of bromine is 2. Sorry, not 1, 2. For n carbon here, number of bromine is 2. Okay. So what you can take is number of carbon by number of bromine equal to n by 2 equal to 3:1 ratio. So you can get what is n. So n equal to 6, right? N equal to 6 means cycloalkene. Cycloalkene. N equal to 6. It is CnH2n minus 2. Cycloalkene. What is the general formula? Cycloalkene. What is the general formula? CnH2n minus 2. Isn't it? Isn't it? Because cycloalkene is isomeric with the alkyne. Cycloalkene is isomeric with the alkyne. Alkyne general formula CnH2n minus 2. So it will be C6H10. C6H10 and now 2 bromine comes. So the formula is C6H10Br2. This is our compound. And we were talking about cyclohexene. We were talking about cyclohexene. And the reaction is like this. Cyclohexene plus Br2 in CCl4, you get a 1,2-dibromocyclohexene. And this is the molecule we are talking about. And the question is, what is the percentage of bromine? What is the percentage of bromine? How to find the percentage of bromine? Percentage of bromine equal to bromine atomic mass 80. 80 into 2 into 100 divided by molar mass 16, 72, 10 and 80 into 2, 160, 170, 242. This is your answer. That is your answer. Percentage of bromine. You can figure out the answer will come 66. Please verify. Please verify whether you get 66 or not. That is the answer. So once again, it is not commented, it's only commented cyclohexene. It's only commented cyclohexene. Which cyclohexene? Not given. Okay. But there is a hint given. Carbon-bromine ratio in the product is 3:1. 3:1. And now, for each mole of cyclohexene, there will be 2 bromine attached. From which we can understand, suppose carbon-bromine ratio n is to 2, which is given as 3:1. If there are n carbon, number of bromine is 2. So carbon-bromine atomic ratio, it is n is to 2, which is given in the question 3:1, from which we get what is n, from which we get what is the formula, from which we are able to get what is the percentage of bromine. Okay, fine. Next question. The hydrocarbon P, C4H8 on reaction with HCl an optically active compound Q, C4H9Cl, which on reaction with 1 mole ammonia give compound R. R on diazotization followed by hydrolysis gives X, PQRS. So you have a hydrocarbon C4H8. On reaction with HCl, you get a optically active compound Q. That is an important hint. Q is optically active. That is a very important hint. Q is optically active. Is this optically active? No. Here Q is not optically active. So eliminate. Here Q is not optically active. Eliminate. Here Q is optically active because it is 1, 2, 3, 4. 2-chlorobutane. 2-chlorobutane contain a chiral center. Once again here. So we get the answer. Here we get the answer. This is optically inactive. So just by analyzing this part of the question, we get our answer. Just by analyzing the nature of Q, we get the answer. Because there is only one choice where Q is optically active. Okay. So let us verify. Let us verify. The compound given 2-butene. This is 2-butene. 2-butene, that is P, treated with HCl, you will get 2-chlorobutane, which is optically active, and that is Q. On reaction with 1 mole ammonia, give compound R. Is it compound R correct? Compound R is correct when this is treated with ammonia. When this is treated with ammonia, chlorine replaced by ammonia, and you get this. This is R. Perfect. And R on diazotization followed by hydrolysis. You see, it's an aliphatic amine. Aliphatic amine upon diazotization. Aliphatic amine upon diazotization, and you will get alcohol because aliphatic amines, aliphatic diazonium salts are unstable, and you get alcohol. That is the final product. So all reactions matches with option 3. Moreover, simply analyzing the indication about Q, we get our answer because none of the option have Q optically active other than option 3. Okay, fine. Next question. Again, there is a sequence given, we need to identify A. There is a sequence given, we need to identify A. A hydrogen, 2 mole hydrogen, platinum, you get this product. One is okay, one is okay because there is one double bond here, one double bond here, one hydrogen here, one hydrogen here. Upon reduction, you will get the product given over the top. And what about this? This when treated with the KMNO4. This when treated with the KMNO4, you don't get this. So one is out. You see, this is what given 1. This is what given 1. This when treated, see, this part is okay. This part is okay when this molecule treated with 2H2, you will get this, no problem. But this is not okay. This when treated with KMNO4, you see it's going to break over here. And this carbon will turn COOH. This carbon will turn COOH. And this carbon will turn COOH. And it will be breaking over here. This carbon will turn keto group. This carbon will turn keto group. So you don't get this product. So option 1 is out. What about option 2? Option 2. Option 2 once again. In fact, option 1, 2, 3 and 4. all choices are fit for first reaction. All the choices, you look at option 4 also, there are two double bond. There are two double bond. There are two double bond. All the choices are fit for first reaction with hydrogen, nickel or platinum. That is fit. Second reaction actually decides our answer. What about option 2? Option 2 is the correct answer. Option 2 is the correct answer. Just have a look at. Suppose if you take option 2, you see the molecule given. This is the molecule given. And you see what will happen if it is treated with the KMnO4. If you treat this with the KMnO4, what's going to happen is it's going to break over the double bond. It will break over the double bond. It's going to break here and it's going to break here, isn't it? And now, what will be the result? What will be the result? You know the oxidation result. This carbon will turn COOH and this carbon will turn COOH and this carbon will turn COOH and this carbon will turn COOH. That means the final product will be this carbon COOH is going to break over here and this carbon COOH is going to break over here, this carbon and this carbon, and these two carbon will become oxalic acid COOH, COOH, and is matching with our question, and the answer is option 2. And about option 3 and 4, you can verify what will be the nature of product. For example, option 4 if you take. Option 4 if you take, what will be the product obtained? It's going to break here, it's going to break here. You will get COOH, please verify. COOH, isn't it? COOH, COOH. This is the product obtained if you take option 4. You see, this carbon and this carbon will turn COOH. This carbon and this carbon will turn COOH. Such a carboxylic acid you get if you take option 4. Fine. So the correct answer is option 2. Option 2 is correct answer. Okay. Next question. Question number 42. Which of the following reaction is not correctly represented? Not correctly represented. That is the question. Option 1, it is Sandmeyer's reaction. It is correctly represented. Option 2. Option 2 is the answer. Option 2 is the answer. What is option 2? You see why it is an answer. Have a look at the reaction. It is CH3 over here and you have a double bond over here and it is treated with Br2 in presence of light. Please understand, it is free radical reaction. It is free radical bromination reaction. And free radical bromination reaction, what will be the product obtained in the given molecule? It should be an allyl bromide. It should be an allyl bromide. Bromine should be coming. Bromine should be coming over here. This is allyl carbon or over here. That should be the product. So the final product should be like this. There is a bromine coming here and a double bond here, and it can be over here also a bromine coming here. So this is allyl bromide. So allyl bromide will be the major product, where you can see in the product bromine is attacking over here. That is wrong. So second reaction, it is wrong, and that is our answer. The question is not correctly represented. Second reaction, the product should be allyl, and this is a tertiary allyl where the dominant will be there, and this is only secondary allyl. So here there will be dominant attack, and that should be the product, where the given product is bromine coming over here. What about third one? Toluene, Bromine iron darkness, that is electrophilic aromatic substitution reaction. You get orthopara bromotoluenes, correct answer, because bromine is orthopara directing in the benzene ring. Right? Sorry. CS3 group is orthopara directing, and a bromine may come here. That is a correct reaction. What about option 4? Option 4, this is free radical reaction. Again, this is free radical reaction. This time the attack will happen on the side chain. If substituted benzene compounds are taken, treated for bromination, treated for halogenation in presence of light, you can say it will undergo free radical substitution and the reaction occurs at a side chain. And this is perfect. Here it should come on allyl position. That is wrong. And we want the wrong reaction. Okay. Next one. Question number 43. To make a correct matching between the compound given, the name given and corresponding example. Name given and corresponding example, we need to make a matching. And what makes the correct matching? Vinyl chloride. This is vinyl chloride. So A with 3. So this is out. Benzyl chloride. This is benzyl chloride. So B with 4. A3B4. We don't get the answer. Alkyl chloride. This is simple alkyl chloride. So C with 2. And that gives us the answer first choice. What about D? Allyl chloride. This is allyl chloride. So D with 1. That is the perfect matching. And a very simple question regarding the classification of alkyl halide part. Haloalkane chapter, various classification from where we find this question. Okay. Next, very simple question, direct question only. Next. Question number 44. Again, we have statement based question. Two statements are given based on a molecule. A molecule. So what will be the correct answer? What about statement 1? Carbon-chlorine bond is stronger in CH2CHCl. CH2 double bond CHCl than CH3CH2Cl. This is correct. Here the carbon-chlorine bond is stronger because mesomeric effect, resonance. You see, there is resonance. The lone pair of electron in carbon involved in resonance. There is a partial double bond character between carbon and chlorine. Vinyl halides involves mesomeric effect. Number 1. Number 2, this is sp2 carbon. On the other side, that is sp3 carbon. And sp3 carbon is less electronegative. This is more electronegative, and that will pull the electron density towards it, causing a decrease in bond length. So number 1, due to resonance, there is a partial double bond character. Number 2, since it is sp2 carbon, it has got more electronegativity, pulling the electron density towards it, causing a shorter bond length. So definitely statement 1 is correct. What about statement 2? The given optically active molecule on hydrolysis gives a solution that can rotate plane polarized light. The given optically active molecule, this is optically active. This upon hydrolysis, it will undergo SN1 mechanism. it will undergo SN1 mechanism and you will get a racemic mixture. You get a PH, COH, and here you have ME, and ET. This is retention product, and there will be an opposite molecule. This is undergoing SN reaction, means this is the product obtained. Chlorine will be replaced by OH. But remember, you get a equimolar mixture of dextro and levo. You are getting a racemic mixture. You are getting a racemic mixture. Why? Because it is SN mechanism. SN mechanism, it is followed by this chlorine goes and you get a carbocation. That chlorine goes and you get a carbocation. This is the carbocation you get. MEET, this carbocation you get. And this carbocation will be attacked by OH minus during solvolysis. The OH minus may be attacking this side. The OH minus may be attacking the other side. The planar carbocation, OH minus may be attacking this side or this side. And that is what SN1 mechanism, front side attack or back side attack. And there will be 50-50 chance of retention and inversion. There is a 50-50 chance of getting dextro and levo. And if it is perfectly racemic mixture form, how can we say that it shows optical isomerism? It will not be rotating the plane polarized light. It can rotate plane polarized light. It is wrong. As it undergo SN1 mechanism, please have a look at this is tertiary compound. A tertiary compound undergoing hydrolysis, it will undergo SN1 mechanism. There will be 50-50 chance of retention and inversion. There will be 50-50 chance of getting dextro-levo. There is a chance of getting racemic mixture, and racemic mixture will not show optical, will not rotate the plane polarized light, because there is 50% this and 50% this. 50% dextro rotating the light to right. Imagine. The other 50% levo will rotate the light to left, and there is no net optical rotation. That is what racemic mixture. Racemic mixture does not cause a net optical rotation because of external compensation. One molecule, whatever rotation given, cancelled by the next molecule. Whatever dextro give a rotation, cancelled by the levo molecule, and they are in equal quantity, and they are enantiomers. Okay. So this statement is wrong. So first statement correct, second statement wrong. Option 1 is the correct answer. Option 1 is the correct answer. First statement correct, second statement wrong. Okay. Next question. Again, you have a sequence given. What is the major product? What is the major product? So the given compound treated with zinc, there will be dehalogenation. Zinc will take away the 2 bromine, and the product after first reaction, it will be a double bond over here. This is the product after first reaction. Now the second reaction, it is attacked with HBr. It is attacked with HBr. So the first step, it is protonation. It will give you a carbocation. You will get a carbocation, say over here, or it can be a carbocation, say over here. There are 2 possibilities. It can be carbocation here, or it can be carbocation here. Right? And there can be a bromine coming here. There can be the bromine Br minus coming here. You get a product. Which product? This one, right? Yeah, this one. This one. This is the product when bromine is coming here, but that is not the major product. Now Br minus may come here. Br minus may come here. Do we have the product? Yes. This, no, no, no. No, this is the product. This is the product, number one. Again, that is not the major product, right? Now, this carbocation can undergo a rearrangement. This carbocation can undergo a rearrangement. The hydrogen migrate over here. You get a rearranged carbocation. You get a rearranged carbocation like this. This is secondary carbocation. This again is secondary carbocation. That's why I said that is not going to be the major product. There is a chance of getting tertiary carbocation. There is a chance of getting tertiary carbocation. And this is a tertiary carbocation, and where bromine comes, you get a product. And there is one more possibility. A hydrogen from here is migrating and you get another carbocation. That is also tertiary. That is also tertiary. This is also tertiary carbocation. Where the Br minus comes, you get the product. These two are the possibilities. Either this or this will be the possibility of major product, because that forms a tertiary carbocation. That means a bromine coming over here. It can be 3 correct answer. A bromine coming over here, 2 correct answer. So the competing choices are 2 or 3, because here it forms a tertiary carbocation. If this is forming, you get a 3. If this is forming, you get a 2. So which is the answer? 3 or 2? That is decided by a relative more stability of the given 2 carbocation. The relative stability of these 2 carbocation will decide which is going to be the major product. And that can be understood by hyperconjugation. You see, this is carbocation. This is alpha carbon. There are 2 alpha hydrogen. This is alpha carbon. There are 3 alpha hydrogen. This is alpha carbon. There are 2 alpha hydrogen. 3 plus 2, 5 plus 2, 7. There are 7 alpha hydrogen over here. Coming on to this side. This is alpha carbon CH2. This is alpha carbon CH2. This is alpha carbon CH2. There are 6 alpha hydrogen over here. So definitely the possibility is this product, and the final product will be, the major product will be this one. And that means third choice will be our correct answer. Right? So when the given molecule treated with the zinc, you get a alkene. Dehalogenation reaction we learned in the preparation of alkenes. So that is first part. After that, there is a core issue. The given alkene undergoing protonation, first you get 2 carbocations. They are secondary in nature. So just out. And that secondary carbocation undergoing rearrangement, there are possibility of tertiary carbocation. Again, there is an issue. There are 2 types of tertiary carbocation. And which tertiary carbocation will be leading to the major product, we need to check. And the winner will be this one, because this carbocation is more stabilized by 7 alpha hydrogen atoms available. There will be 7 hyperconjugative structures, and this carbocation will be a slightly more stable compared to that, and the reaction will be traveling on that path, leading to the final product. Okay, next question. Question number 46. Consider all the structural isomers with the molecular formula C5H11Br separately treated with the KOH to give C5H11Br means bromopente, isn't it? It is bromopente. Bromopente. Separately treated with the KOH to give respective substitution product. without any rearrangement. Without any rearrangement. The number of products which can exhibit optical isomerism from these is, you see, this is the molecule. This is C5H11Br2. 1, 2, 3, 4, 5 carbon atom. Right? C5H11Br, not Br2, Br. This is what the compound. But this is not the answer, because this, when hydrolyzed with the KOH, this bromine goes and you get OH. And that is none of our business. If this is optically active, the obtained product will be optically active. So this is not our product. I mean the compound. But there can be a molecule like this. This is optically active. This is optically active as there is a chiral center. And that bromine, when replaced by OH, that will be optically active. So this is number 1 in our list. What about next? This is another possibility, but that is not optically active, because this group and this group are same. These two groups are same, so it is achiral, not optically active. This is not in our list. Next one, so this is over. Next one, it is this. Suppose a bromine coming like this. Suppose a bromine coming like this. This is 1, 2, 3, 4, 5 carbon atom. Now this carbon is optically active and this is in our list, right? Now, do we have anything else? Imagine bromine coming here. Imagine bromine coming here. That is also optically active. This is a chiral center and that is in our list. A bromine can come here, no? The bromine can come here. But no use. But no use. A bromine coming here, or no use, because these two are same. It is not optically active. Bromine can come here, no? It can come here, here. But again, no use. It is not showing chirality. What else? What else? This is another one. 1, 2, 3, 4, 5. This is another one, but that is also achiral. So this is not in our list. This is achiral, not in our list. This is achiral, not in our list. And this is in our list number 1. This is in our list number 2. This is not in our list. And this is in our list. So there are 3 molecules. There are 3 molecules without any rearrangement. There are 3 molecules which can lead to optically active forms upon hydrolysis or without hydrolysis also. Upon hydrolysis, that doesn't make any other sense. Bromine replaced by OH. That's it. So the answer is 3. There are 3 compounds which show optical activity. So the direct question is, how many of the molecules are optically active? That is a point. From C5H11Br. That is the question. Okay? Yes. Next. The correct order of reactivity of CH3Br in methanol with the following nucleophile is. So the medium is protic medium. In protic medium, how comes the nucleophilicity order of halogens in particular? Halogens in particular, I think everybody know. The nucleophilicity in protic medium, it is I minus, Br minus, Cl minus, F minus. This will be the order in protic medium. Because in protic medium, the very small F minus undergo association. I mean it is interacting for hydration, isn't it? F minus is very small, it undergo hydration, and the nucleophilicity character is affected by polar protic medium, and it is minimum. F minus. I minus is maximum. I minus is maximum. While in aprotic medium, it is opposite. While in aprotic medium, it is opposite. It is F minus, Cl minus, Br minus, I minus in aprotic medium. So here, since it is a protic medium, Since it is a protic medium and we have two more people to compare, it is I minus maximum, no doubt. And even in the choices, no doubt, I minus is maximum. A knowledge I minus maximum does not help you to get the answer. And F minus will be minimum. F minus will be minimum. And there you get the answer. I minus maximum, F minus minimum will take you to the answer. And what about ethoxide and phenoxide? What about ethoxide and phenoxide? It's very simple to categorize CH3, CH2OH and C6H5OH. You know, this is more acidic. Phenol is more acidic than alcohol. We studied. We know that. Phenol is more acidic than alcohols. So what about their conjugate base? What about their conjugate base? CH3, CH2O minus will be more basic than C6H5O minus. So this will be the order of basic strength. A strong acid will have a weak base. A strong acid will have a weak base. So relative acidic strength is like this. Therefore, relative basic strength will be like this. And the basic strength can be taken as nucleophilicity order, isn't it? So this will be a better nucleophile. This will be a better nucleophile than this. And our question is correct order of reactivity of CH3Br in methanol with the following nucleophiles. So this bromine replaced by iodine fast, no doubt. Iodine fast and fluorine least. Iodine fast, fluorine least. That is fixed, we get our answer. And regarding these two, this is a better nucleophile than this, because this is a stronger base than this, because this is a weak acid than this. So conjugate acid-base pair concept will help you to understand how comes the order between ethanol and ethoxide and phenoxide. So ethoxide, alkoxide is a better nucleophile than phenoxide. Keep it in your mind. Alkoxide is a better nucleophile than phenoxide. Okay. And hence the answer. And this is also very, very important. How the halide ions are behaving in polar protic medium and aprotic medium. That's very, very important. Normally, we will encounter a question based on protic medium. Okay. Next question. Here you have a note. Here we have a note on whatever I said. The general order in polar protic solvents, the nucleophilicity of halides. This is the nucleophilicity of halides in polar protic solvents. That will be a general order. This trend is attributed to size and polarizability of halide ion. Size and polarizability of halide ion, right? Larger ions like iodide are less solvated. Larger ions like iodide are less solvated and can donate electron density more effectively than smaller ions like fluoride, which are more tightly held by solvent molecules. Fluorides are very small in nature and they are more tightly held by solvent molecules in polar protic medium. What about in aprotic medium? While in aprotic solvents, the trend will be reverse. In these solvents, halide ions are less solvated, allowing the more basic fluoride ion to act as a stronger nucleophile compared to larger halides. As all of you know, HF is a weak acid, F minus is a strong base. HF is a weak acid, F minus is a strong base. Okay, right. Question number 48, statement based question. Compared to chlorocyclohexane, which of the following statements correctly applied to chlorobenzene? So the encountering is between chlorocyclohexane versus chlorobenzene. This is our encountering scenario. So compared to chlorocyclohexane, following statements correctly apply. Following statement correctly apply to chlorobenzene. Let's see. Option A. The magnitude of negative charge is more in chlorine atom. Here, the more, to chlorobenzene. The magnitude of negative charge is more on chlorine atom. No, it's a wrong statement. It's a wrong statement. There is resonance. There is resonance. You can see here the chlorine is, the electrons are localized. There is no resonance. While here there is resonance. There is resonance, and due to resonance, the magnitude of negative charge more on chlorine atom. It is more on chlorine atom. Due to resonance, it is less polarized. It is less polarized. Here you have C plus and delta plus, delta minus. Here you have delta plus, delta minus. Here that is less. It is less polarized because that lone pairs involved in resonance. The lone pairs involved in resonance. So magnitude of negative charge is more on chlorine atom. Wrong. It is rather due to resonance. I am sure you remember. It is turning like this. It is turning like this. This is the resonating structure. So first statement is wrong. Second statement, carbon-chlorine bond has partial double bond character. That is correct. That is correct. There is a partial double bond character between carbon and chlorine in chlorobenzene due to resonance. B is correct. So A wrong, B correct. We don't get the answer. Carbon-chlorine bond is less polar. This is correct. This is correct. Carbon-chlorine bond is less polar, and these two are complementary comments. Carbon-chlorine bond is longer due to repulsion. Carbon-chlorine bond is longer due to repulsion between delocalized electron in aromatic ring. That is wrong. This is shorter bond. This bond is carbon-chlorine bond in chlorobenzene is shorter in nature. Two reasons. One, partial double bond character due to resonance. Two, this carbon is sp2 carbon. This is an sp2 carbon and this is an sp3 carbon. An sp2 carbon will pull the electron density towards it more and the bond length decreases. Option D is a wrong statement. Carbon-chlorine bond is longer due to repulsion. Wrong. It is shorter. It is shorter. And we get the answer. The answer is option 3. What about option E? What about option E? Carbon-chlorine bond is formed using sp2. That's correct answer. That is correct statement. So the answer is option B, C, E. I think it is perfect. Next. 49. The correct order of rate of reaction. Correct order of rate of reaction. By the nucleophile, with a nucleophile by SN1 mechanism. With the SN1 mechanism. SN1 mechanism means it undergo carbocation mechanism. It undergo carbocation mechanism. That is SN1 mechanism, isn't it? So we have to check the relative stability of carbocation. We need to check the relative stability of carbocation since it is mentioned SN1 mechanism. Let us verify the stability of carbocation. You see, these two are bicyclo ring, and in a bicyclo ring, I think everybody know this is a bicyclo ring, and imagine this bromine goes and this carbon turn carbocation, this is less favorable. A positive charge on bridgehead carbon is unfavorable. So these two molecules are actually unfavorable, I would say. These two molecules are coming last, I would say. Because upon leaving that halogen, you get a carbocation, and carbocation formed is on bridgehead carbon. This is called bridgehead carbon. In a bicyclo unit, this carbon and this carbon, it is called bridgehead carbon. In a bridgehead carbon, a positive center, any sort of polarity is not appreciated. It doesn't want, sorry, not polarity, planarity. Any sort of planarity is not appreciated. It is not appreciating a double bond in that region. It is not appreciating a positive charge in that region. It is not appreciating a free radical in that region, because forming a carbocation, it becomes planar. Having a free radical, it becomes planar. Coming a double bond, it becomes planar. So planarity is not appreciated in a bridgehead carbon. So I would say molecule 1 and 2 will be last, and 3 and 4 will be high. No doubt 4 will be maximum, because this carbocation highly stable due to resonance. You see, this carbocation, that is the fourth one, it is triphenyl methyl carbocation. Imagine this bromine goes, you get a carbocation here. Here, this is a triphenyl carbocation, triphenyl methyl carbocation, which is highly stable. And that will go for SN1 mechanism very fast. So 4 should be maximum. 4 should be maximum. You see the competency of the options. This only is out. 4 is maximum. After 4, it will be 3. After 4, it will be 3. This is out. So 1 or 3. 1 or 3. Now coming to 1 and 2. So these two are high. We get the 2 choices out. 2 choices out by knowing these two are less and these two are more. And what about 1 and 2? 1 and 2. Both are bicyclo molecules. Both are bicyclo molecules. Both are identical with a small difference. And that difference takes us to the answer. That difference takes us to the answer. Look at the first molecule and second molecule. This is first, and this is second. I would say this will be last. 2 will be last. And the answer is third choice. This will be the correct answer. Why? Why 2 is last? 2 is last because this is more strained system. Here you look at the ring size. You look at the ring size over here. You have carbon, 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 forms a pentagonal ring. Here it forms carbon, 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 carbon. There is a greater number of carbon forming a hexagonal type ring, and the strain is less. This will be more stabilized than this. Both are unstable. Both carbocations are unstable because it is forming a bridgehead carbon, number 1. But relatively, this is better. Relatively, this is better compared to this, because that molecule is bit more strained. This molecule is bit more less strained. So this will come after 3. After 3, it will be 1 and 2 will be last. See the beauty of those molecules and its order given. Out of the 4, 2 is one category, 2 is another category, and that helps us to identify 2 choices. And the remaining 2 choices we need to understand by the nature of molecules 1 and 2, a relative comparison of molecules 1 and 2. Okay, yes. Next question. The correct order of reactivity of the following benzyl halides. towards reaction with the KCl. Towards reaction with the KCl, once again it is SN reaction. SN reaction. All are benzyl. So once again it is benzyl carbocation highly stable. The stability of benzyl carbocation will give you the answer. The stability of benzyl carbocation is going to give you the answer. Okay. So how it comes? Let's have a look at. See, this bromine, when broken, you get a benzyl carbocation. This is benzyl carbocation. Similarly here, this is benzyl carbocation. Here and here. And how come the stability of carbocation? Greater the stability of carbocation, greater the stability of carbocation, greater the chance of that reaction. Okay, which is highly stable. Which is highly stable. This is electron donating group. Electron donating group stabilizes the carbocation. This is also electron donating group. This is electron withdrawing group. This is electron withdrawing group, of course. So these two will be less and these two will be more. I mean the reactivity. The reactivity depends on stability of the carbocation. A carbocation more stabilized by electron donating group. So presence of electron donating group stabilizes the carbocation and the reaction occurs more in that direction. The stability of intermediate. When the stability of intermediate is more, the chance of reaction in that pathway will increase. Because every reaction proceeded in a direction of stability. So electron donating group increases the stability of carbocation. So out of 1 and 2, out of A and B, sorry, A, B, C, D, A, B will be one category because they are electron donating group, OH group and NH2 group. While C and D, it is nitro group. That will be less. Now, out of A, B, which is better? OH, NH2. No doubt it is NH2. So B maximum. B maximum. So this is out, this is out. B maximum. And after B, it will be A. After B, it will be A. You don't get the answer. And after that, is it D or C? Is it D or C? No doubt. First A, then first B, then A. After that, it will be D because this electron withdrawing group is at a meta position. An electron withdrawing group at a meta position does not make much influence. Its influence is very high at ortho-para position. This is an electron withdrawing group at a para position. And its electron withdrawing effect is maximum. And electron withdrawing group, please understand, destabilizes the carbocation. An electron withdrawing group at a para position highly destabilizes the carbocation. And that will be last. I mean, C will be last. So the answer is option A. Option A. Out of AB, B maximum. Out of AB, B maximum. After that, it is A. Out of CD, C minimum. Because C and D contain nitro group. But in C, nitro group is at a para position. And the electron withdrawing effect of NO2 group is high at a para position. And that destabilizes the carbocation highly and the reactivity decreases to the minimum. Hence the answer. Right? There are 4 compounds given. Percentage of carbon in the one which exhibit optical isomerism. So first we need to find out the one which show optical isomerism. N-propyl chloride. This is N-propyl chloride. There is no optical isomerism. Isopropyl chloride. This is isopropyl chloride. There is no optical isomerism. Secondary butyl chloride. That is the compound. This shows chirality. So this is the molecule we are talking about. Neopentyl chloride. This is neopentyl neopentyl chloride. 1, 2, 3, 4, 5. This is neopentyl chloride. There is no chirality. So chirality and optical isomerism shown by secondary butyl chloride. Secondary butyl chloride. So we need to check the percentage of carbon in secondary butyl chloride. That is C4H C4H9Cl, correct? CH3, CH, CH2, CH3. Yes. So C4H9Cl, what is the percentage of carbon? Please find out. Percentage of carbon, 4 carbon. So it is 48 divided by 48, 957 plus 35.5. 92.5. 92.5 into 100. Isn't that correct? Yes. So nearly 50%, but there are two choices. Option 1 ഉണ്ട്, 2 ഉണ്ട്. Nearly 50. നോക്ക് 50, nearly 100. അല്ലേ? ശരിയല്ലേ? So what will be the correct answer? Is it below 50 or above 50? 48 എന്ന് പറയുമ്പോൾ 96. ഇവിടെ 96 ആണെങ്കിൽ 50%. If it is 96, 50%. It is 92. So just above 50. അത് രണ്ടെണ്ണം ഉണ്ടല്ലേ? 52 ഉണ്ട്, 56 ഉണ്ട്. It will be 52%. It will be 52%. Slightly above 50. Slightly above 50. Option 1 is the correct answer. So we need to understand from the given molecule, we need to understand which is optically active, number 1, right? After understanding that, check the carbon percentage. So out of the 4, this is optically active. Adinte carbon percentage C4H9Cl ennaanu varu. So the percentage will be like that. Easily calculatable data. Next. 52. There is a long sequence is given. Number of bromine atom in the final product. So you need to write the entire sequence and get the final product and get number of bromine atom in that final product. That is the question. Let's see one by one. So first reaction. You are given with the nitrobenzene treated with the bromine and a Lewis acid. So it will be ESR, electrophilic substitution reaction. This will produce a Br plus and it will be attacked by benzene ring. So after first reaction, you get a bromine substituted. Since it is nitro group is meta-directing in nature, so you get a bromine here. Nitro group is meta-directing in nature. So you get a bromine at a meta position after first reaction. Now the second reaction, tin with HCl will reduce NO2 to NH2. So the second product, the product after the second reaction SnHCl, NO2 turn NH2. This is the product after second reaction. pH neutralization. pH neutralization means neutral pH. pH neutralization means neutral pH, nothing else. Since here we deal with an acid medium, neutral pH. Otherwise, this will be protonated and it may give different product. அடுத்தது fourth one, bromine water. Aniline with the bromine water, there will be a bromine coming here, here and here. Tribromoaniline. So after fourth reaction, the product will be like this. We have an NH2 group here. Ivada oru bromine varum. Ivada already we have a bromine. Ivada oru bromine varum. Here also you get one bromine. This is the product after fourth reaction. Now fifth reaction, NaNO2HBr, you get a diazonium salt. You get a diazonium salt. NH2 will turn diazonium salt, N2 plus Br minus, and all bromine as such we have seen earlier like this. And now the last one, Sandmeyer's reaction. And Sandmeyer's reaction, this will be replaced by bromine and we have the final end product. This is the final end product P. Nothing but this will replace by bromine. Ivada oru bromine already. Here we have bromine already. Here we have bromine already. Here we have bromine already. So number of bromine atom. Number of bromine atom in the final product P. 1, 2, 3, 4, 5 bromine atom present. And the answer is option 3. There are 5 bromine atom. Okay. I repeat. We start with the nitrobenzene. Nitrobenzene bromination, you get meta-bromo-nitrobenzene. And then reduction to aniline. Nitro group is reduced to aniline. And then we have bromination once again. 2,4,6 tribromo substitution we know. So already one bromine here. 3 more bromine comes. And then diazotization. And then Sandmeyer's reaction. 1 more bromine comes. So the total bromine at the end of the show, 5. Okay. Yes. Next question. The reaction which produce alcohol as product. The reaction which produce alcohol as product. A methane with oxygen, molybdenum oxide. If it is copper catalyst, you get methanol. Selective oxidation reaction, controlled oxidation reaction. The properties of alkane. Alkanes, we learn combustion reaction, incomplete combustion reaction. And then there are 4 important controlled oxidation reaction given. Number 1, methanol heated with the copper catalyst. Methane heated with the copper catalyst, you get a methanol. Methane heated with the molybdenum oxide, you get a methanol. This is methanol, HCHO. So that is not the answer. Now again those reactions. Ethane with the manganese acetate, you get ethanoic acid. And an alkane containing tertiary hydrogen, when treated with the KMNO4, you get an alcohol. So learn all those reactions. Number 2. So A is not in the answer. So 2 choices out. B. Ethane with the manganese acetate. You get ethanoic acid. You get CH3 COOH. Ethanoic acid. We want alcohol. B not in the answer. A not in the answer. B not in the answer. We get the answer option 4. C and D. Let us verify. C. This is an alkane with the tertiary hydrogen. Alkane with the tertiary. Normally alkanes resist oxidation. Alkanes means paraffins. They are unaffected by acids, alkalis, oxidizing agent, reducing agent, etc. So normally alkanes resist oxidation. But an alkane with the tertiary hydrogen, when treated with the KMNO4, it will give you an alcohol. And the product obtained will be, in this case, the product obtained will be CH3, CH3OH. You get a tertiary butyl alcohol, and C is one of our answer as we already got. And D, methane with the copper catalyst, we get methanol. Methane with the copper catalyst, we get methanol. D is an answer. What about E? What about E? This treated with the KMNO4, it is oxidation reaction, is going to break over this, and these 2 carbon will turn carboxylic acid, and your answer is CH3COOH. CH3COOH, CH3COOH. That is the answer in option E. So the answer is C and D. A question from controlled oxidation reaction of alkanes. Again, those 4 reactions, methane, all reactions are available here. Methane with the copper catalyst, 523 Kelvin, 100 atm, you get methanol. methane with molybdenum oxide, methanol, ethane with manganese acetate, ethanoic acid, and alkane with tertiary hydrogen, you get alcohol. These are the 4 controlled oxidation reaction we learned in the textbook. Chapter is hydrocarbon, portion is alkane, preparation, properties, chemical reactions. Okay. Next. 54. Consider the following reaction sequence. Compound Y develops characteristic color with a neutral FeCl3 solution. So Y should be phenol. Y should be phenol or its derivative. Y should be phenol or its derivative. Compound Y develops characteristic color with the neutral FeCl3 solution. Identify incorrect statement from the following for above sequence. Compound X, vapor density given. Compound X, vapor density given. You know, molar mass equal to 2 times vapor density. So 2 into 47, it is 94. 94. Compound 94. Compound 94X. And look at the reagents. Carbon dioxide, NaOH heating at high pressure. Hope you understand the reaction. It is Kolbe's reaction. It is Kolbe's reaction. And 94, the compound can be phenol, right? Let us verify. X can be phenol. What is the molar mass? C6H5OH. 77, so 78 plus 16, 94. Yes, this is the compound X. This is the compound X, that is phenol. Phenol treated with the carbon dioxide NaOH. This is first treated with NaOH. You get sodium phenoxide. You get sodium phenoxide, and that will attack the weak electrophile carbon dioxide. And maybe everybody remembering, you get Kolbe's reaction. This is Kolbe's reaction, and upon acidification, you get salicylic acid. This is salicylic acid. Once again, it is phenol derivative. Compound Y develop characteristic color with the neutral ferric chloride. This is Y. Perfectly okay. Because it is a phenol derivative, actually there is a phenol group. It can give characteristic color with the neutral ferric chloride. And it is nothing but salicylic acid. And the reaction is Kolbe's reaction. So X is phenol, and Y is salicylic acid. Now, what is our question? Incorrect statement. Statement 1. Both the compounds X and Y will burn with the sooty flame. Yes, both are aromatic. That is aromatic and this is aromatic. They will burn with the sooty flame. Option 1 is correct. We want incorrect. Compound Y will dissolve in sodium bicarbonate and evolve gas. Correct. This is a carboxylic acid. A carboxylic acid, when treated with the sodium bicarbonate, there will be brisk effervescence liberating carbon dioxide. So second statement is also correct. Third one. Both the compounds X and Y will dissolve in NaOH. Yes, they will dissolve in NaOH. This can dissolve in NaOH. This group can neutralize. This group can neutralize. And this group can neutralize. Both the phenol and the carboxyl group can dissolve in NaOH. They are sufficiently acidic to give a neutralization in NaOH, and the correct answer should be fourth choice. Let us verify. Correct answer should be fourth choice. X is more acidic than compound Y. Wrong. This is more acidic than that. Salicylic acid is more acidic than that. Which one? Phenol. No doubt about it. This is a carboxylic acid. This is a carboxylic acid and that is phenol. A carboxylic acid is more acidic than phenol. No doubt about it. So, compound X more acidic than compound Y is a wrong statement and that is our answer because we want incorrect statement. Okay? Fine. Let's move on to next question. From the following, how many compounds contain at least one secondary alcohol? At least one secondary alcohol. Let's verify. Secondary alcohol. This is carboxylic acid. This is a primary alcohol. This is a primary alcohol. Out. This is a primary alcohol while this is a secondary alcohol. So, in. This is a tertiary alcohol. This is also a tertiary alcohol. Out. This is a primary alcohol, while this is a secondary alcohol. This is a secondary alcohol, while this is a tertiary alcohol. Anyway, it contains tertiary secondary alcohol in. This is a secondary alcohol, while this is a tertiary alcohol. Anyway, it is in. This is a primary alcohol. This is a tertiary alcohol. And this is also tertiary alcohol. Out. So, how many in? 1, 2, 3. 1, 2, 3. Second choice is the correct answer. There are 3 molecules which contain secondary alcohol. Simple question, but some people may make a mistake, sometimes due to overconfidence, sometimes due to some silly mistakes. Yes. Next question. The unsaturated ether on acidic hydrolysis produces carbonyl compound as shown below. Based on this, predict the solution reagent that will help to distinguish P and Q obtained in the following reaction. So here what will be the reaction? That is hydrolysis. Imagine it is breaking here minus. No, it will break on the other side. Anyway, that doesn't make a matter. So this is minus and this is plus. Both are identical only. So here you get, so here there will be H plus and here there will be OH minus. So the result is CH3, CH double bond CH OH. And it will undergo tautomerization. This will undergo tautomerization. And the result is CH3, CH2, CHO. This is the compound number 1. What about on the other side? Here you get CH3, COH, double bond CH2. Once again, there will be tautomerization. It will lead to CH3, CO, CH3. This is compound number 2. So these are P and Q. These are P and Q. And what is the question? The reagent that will help to distinguish P and Q, aldehyde and ketone, propanol, propanone. One is propanol, one is propanone. It can be distinguished by filling solution. It can be distinguished by filling solution. Filling solution will oxidize. Filling solution is a mild oxidizing agent. I think everybody know aqueous copper sulfate and aqueous sodium potassium tartarate. That is filling solution. A mild oxidizing agent, milder than Tollens reagent. It will oxidize aliphatic aldehydes, not ketones. You will get a red precipitate. It will oxidize aliphatic. It will oxidize this, not this. So filling solution will oxidize this, not this. That is the answer. Lucas reagent, no reaction. NaHSO3, no reaction. DNP will react with both. This will react with the P, not with the Q. Hence the answer. There is no reaction, Lucas reagent. Lucas reagent is for alcohols. And NaHSO3, saturated NaHSO3, both will react. Both will react. Addition of NaHSO3, both will react. Once again, the reaction will be less with the ketone. It will react more with this, less with this. The equilibrium is more to left side if you are dealing with the ketone, but it will react. And 2,4-DNP, both will react. If you take P and Q, this will be the answer. This will be the answer because P, filling solution, will react and Q, no reaction. Okay. So understanding the hydrolysis product and thereafter the tautomerism is very, very important. And then we get the answer by the distinction usual reactions. Okay. அடுத்தது. Next. A hydroxy compound X with the molar mass 122 gram per mole is acylated with the acetic anhydride using a large excess of reagent, ensuring complete acetylation of all hydroxyl group. The product obtained has a molar mass 290 gram per mole. Number of hydroxyl group present in the compound. We did many questions on this idea. It's a quantitative estimation of number of OH groups, or it may be for estimating number of NH2 group also. So in a molecule, number of OH group and of course number of NH2 group you can easily estimate by acetylation. And hope you remember the calculation many times we did in the class. The calculation is, it is the the molar mass of the final product 290 minus molar mass of the initial compound 122. How much? 8, 6, 2, isn't it? No, 1. So, yes, 168. That is the difference. Now, 168 divided by 42. 168 divided by 42. 4 is the answer. 4 is the answer. This calculation we did multiple times during estimation of OH group, during estimation of NH2 group. The number of OH groups, number of NH2 groups can be estimated like this. The reactant molar mass given, product molar mass given, take the difference, divide with the 42, you get your answer. Now, what is the logic? What is the logic? The logic is very simple. If you take an alcohol, imagine this is an alcohol taken having one OH group. When this is treated with acetic anhydride, this is acetic anhydride, there will be esterification. This acid group and this undergo esterification, and the product obtained will be OCOCH3. So this hydrogen will be out. From the alcohol group, hydrogen is out and CH3CO group is in. That is acylation product, esterification. That is esterification reaction. Simple esterification reaction, ROH plus CH3COCl, HCl out, and the result is ROCOCH3. So this hydrogen goes and CH3CO group in. Okay. So what is the mass of this group? Mass of this group 2 carbon, 24, 3 hydrogen and 1 oxygen. Etra 24, 34, 40, 43. The mass of this group is 43. Mass of the incoming group is 43. One hydrogen gone. Subtract minus 1. So it is 42 will be the difference for each acylation. Each OH group getting acylated, there will be increase in molar mass by 42. Suppose there is one OH group. After acylation, molar mass will increase by 42. Suppose there are two OH group. Molar mass increase by 2 into 42. Suppose there are three OH group. Molar mass increase by 3 into 42. Suppose there are n OH group. Suppose there are n, this is same applicable to NH2 group also. This is same applicable to NH2 group also. NH2 group treated with CS3COCl or acetic anhydride. This HCl out, and what is the result? RNHCOCH3. Same thing is applicable. One hydrogen gone and CS3CO group in. One hydrogen gone, minus 1. 43 in. CS3CO group molar mass is 43. 43 in. One gone, 43 in. That means the difference is 42. So for each acylation, the molar mass of the product will increases by 42. Okay. Now see what is the logic of this calculation. Now see the logic of this calculation. This is final molar mass. This is initial molar mass. Take the difference, you get 168. And for each group coming, 42 will be the difference. So the difference in molar mass divided by 42 will give you the number of groups. Remember, it's applicable to number of NH2 group also. Same way. So number of OH group in a compound, say for example glucose. When you undergo acetylation, when treated with excess of acetic anhydride, you can definitely understand the molar mass of glucose 180 will increase by 5 into 42. There are 5 OH group in glucose. Each OH group is getting acylated. So 5 CS3CO group in the final product, and hence you know it is pentaacetate is obtained. Pentaacetate is obtained. So what will be the molar mass of pentaacetate of glucose? It is 180 plus 5 into 42. That will be the molar mass of pentaacetate. Is it clear? So looking at the molar mass of the reactant molecule, looking at the molar mass of the final acetated molecule, you can find out how many OH group was there, how many NH2 group was there. It's very simple. I repeat once again. Take the difference between the molar mass, and that difference divided by 42 will give you the answer. Okay, fine. It's a very, very important type of question. Next. Question number 58. You have a mixed ether given. You have a mixed ether given. P. Mixed ether means, you know, unsymmetric ether. So P is a mixed ether. When heated with the excess of hot concentrated hydrogen iodide, produces two different alkyl iodides. Two different alkyl iodides, which when treated with the aqueous NaOH give Q and R. Both Q and R give yellow precipitate with the NaOI. Identify mixed ether. So there is a mixed ether when heated with the excess of hot concentrated hydrogen iodide. Produces two different alkyl iodide. So suppose we are taking this, the alkyl iodide obtained. The alkyl iodide obtained. One is this and one is this. So the alkyl iodide obtained, one this and one pH this. This is the alkyl iodide obtained if you take option A, which when treated with the NaOH giving compound Q and R, this will be converted to this and this will be converted to this. Fine. Both Q and R give yellow precipitate with the NaOI. Both the Q and R give yellow precipitate with the NaOI. Identify the mixed ether. Oh, here there is one more carbon. There is one more carbon. So, this part of the molecule, when treated with the HIXS, this part of the molecule will become like this, and that with the NaOH you get this. This is ethanol, CS3, CS2OH, that is Q and R. This is R. Now, both give yellow precipitate with the NaOI. I hope you understand this is haloform reaction. Getting a yellow precipitate with the NaOI means you are getting iodoform. This will give you iodoform. This will give you iodoform, that this is a methyl carbinol group. This is a methyl carbinol group. A compound with a methyl carbonyl group can give you haloform test. Hope you remember. Which compound gives haloform test? Haloform test is given by those molecules which contain, haloform test is given by those molecules which contain methyl carbinol group or methyl keto group. A molecule contain this or this other than carboxylic acids. A molecule containing methyl carbinol group, CS3CHOH group, or CS3CO group, methyl keto group, other than acids and derivatives part, they will when reacting with the chloroform and alkali, or when they are reacting with the halogen and alkali, you will get a haloform. We have studied haloform test. So, out of this will give you haloform test, no doubt, but this will not, because this does not contain methyl carbinol. This is ethyl carbinol. Have a look at the molecule. This is ethyl carbinol. This cannot, carbinol. This is ethyl carbinol. This cannot give haloform test. So first choice is out. What about second choice? Once again, this part will be converted to ethanol. I mean ethyl iodide. Ethyl iodide, and further it will be converted to ethanol, and that is fit for giving haloform test, while this part cannot. Have a look at the molecule. This is the iodide we get. And that when NaOH treated, you get like this. This is the molecule. This is a tertiary alcohol. That is not a methyl carbinol. That's a tertiary alcohol. That is not a methyl carbinol. And you know, a tertiary alcohol, it is not easy to undergo oxidation. Haloform reaction is a oxidation reaction. So again, this is out. So first choice out, because this part is unfit for our question given. Second question out, because again this part is unfit for our hint clue given in the question. What about third? Third, once again, this part of the molecule will be converted to iodide, and that will give you ethanol, and that is okay. What about the other part? This part of the molecule, you get iodide like this, and that upon hydrolysis, you will get it. Yes, that will be the answer, it seems. That will be the answer, it seems. This is the alcohol we get. This is the alcohol we get. And both contain methyl carbinol group. Let us verify that once again. This is the molecule given. This is the molecule given in option 3. Okay. This undergoing treated with the excess of HI. Excess of HI. You see this part of the molecule, you will get CH3, CH2I, and that is treated with NaOH. You get CH3, CH2OH. This will give you haloform test as it is ethanol. And now this part of the molecule, that is you are going to get this one, this carbon, this one, and that upon treated with NaOH, you will get this. This is a methyl carbinol group. Have a look at that. CH3, CHOH, CH2, CH3. This is a methyl carbinol group, and that can respond to haloform test. Third choice is the correct answer. Third choice is the correct answer. What about fourth choice? What about this is fourth choice. If you take the fourth choice, it is PHI, and that will become PHOH. This cannot give haloform test because there is no methyl carbinol group. What about the other part? That can. This part is okay, this part is unfit. So in the fourth choice, first part is unfit, second part is okay. In the third choice, both part, this is okay, this is okay, and that will be the answer. Third choice, this will be our answer. And coming to first choice, this part is okay, this is unfit. Again, second choice, this is okay, this is unfit. Third choice, both the part are fit for the question hint given. Okay. I hope it is clear. Next, 59. Question number 59. 3,3-dimethyl 2-butanol cannot be prepared by 3,3-dimethyl 2-butanol. Edanadu? Butanol, 2-butanol, 3,3-dimethyl. This is the compound. This is the compound we are talking about. Cannot be prepared by. Cannot be prepared by. Let's have a look at option A. Option A, we have methyl magnesium bromide followed by hydrolysis. So this is Grignard reagent. This is plus, this is minus, this will polarize, minus and plus, there will be attack. An aldehyde reacting with the Grignard reagent, the product obtained will be, this will turn O minus and that will become OH by capturing proton, and here there will be CH3. Here there will be CH3. Yes, so A will give and not our answer. Cannot be prepared by. A will give. How it gives? The Grignard reagent added on this aldehyde system. And you know, higher aldehydes when treated with the Grignard reagent, you get a secondary alcohol. You see, this CH3 group will come here, and this O minus will become OH by capturing proton. So this carbon O minus capturing proton, you get OH, and this methyl group coming on this carbon, you get, this is the product, same product, you can see, same product. So A will give the product and it is out. Oh my God. There is no choice containing A. So they commit themselves. There is A not in the list. What about B? What about B? Let's see. First step, it is protonation. First step, it is protonation. You get the carbocation. You get the carbocation like this. Now there will be a methyl rearrangement to get a different carbocation. This will be the new carbocation. And their OH group is coming means, this will be the final product. This will be the final product in option B. And that doesn't match with our system. This doesn't match with our system. So B will not give that major product. So B is an answer, but we don't have any use because all choices contain B. And they say B is definitely in the answer. Okay. Now, what about C? What about C? C, first step, it is ozonolysis. There is ozonolysis happening. It's going to break over here. And this carbon will contain an oxygen. This carbon will contain an oxygen. And after first reaction, the product will be like this. It seems both the products are identical. You get 2 mole of this product. Okay. And now that is treated with NaBH4. Now this is treated with NaBH4, isn't it? NaBH4. That means a keto group will be reduced to alcohol group and the result will be like this. Is that compound the same? Yes, these two are same. These two are same. So C will give the result. C will give the result and C should not be there in the choice. Cannot be prepared. So C undavan padilla. So answer is either 1 or 4. Actually, we don't have to check D. Actually, we don't have to check D. D is not in the picture. Let us check. Let us check. No need to check. This group will be reduced by lithium aluminum hydride and definitely you are going to get the same compound. You get the same compound. So D will give the product, not in our answer. So in our answer there is B, and what about E? What about E? This compound treated for hydration reaction. E treated for hydration reaction, it is a higher alkyne. So there will be addition of water according to Markovnikov rule. So OH minus will come there and you get like this. There is OH minus and here it is CH2. Now this will undergo tautomerization. This hydrogen will come here and this will come here. And the final product is a ketone. Final product is a ketone and that doesn't match with our answer. That doesn't give the result. This result is not given by E and the answer is option 1. Answer is option 1. So the reaction B and reaction E will not give you the concerned product. And remember, no need to check A and whatever discussion we done on A. Actually, when you are in the exam hall, please be very careful. You need not check A. So A is not in the list. You need not check D. D is not in the list. Even though 5 reactions are given, you need to check only 3 reactions because reaction A and reaction D are not in our picture. Please be very careful. That's why we say always keep an eye in the option. Always you are supposed to keep an eye in the option and avoid unnecessary exercise that you do in the exam hall because time do matter. Okay, fine. Let's go to next question. Statement 1, statement 2, statement 1, statement 2. First statement. Phenol on treatment with chloroform and alkali under reflux condition followed by acidification produces para-hydroxybenzaldehyde as major product and ortho-hydroxybenzaldehyde minor product. Wrong. Wrong. This is Reimer-Tiemann reaction. This is Reimer-Tiemann reaction. Phenol when treated with chloroform and alkali. CHCl3 and alkali, you are getting an intermediate. This is ONA or OKA, O minus, and this will be CHCl2, and that upon hydrolysis, you get salicylaldehyde. You get salicylaldehyde. This is the major product. That means ortho-hydroxybenzaldehyde is the major product in Reimer-Tiemann reaction. First statement is wrong. First statement is wrong. What about second statement? The mixture of para-hydroxybenzaldehyde and ortho-hydroxybenzaldehyde can be separated by steam distillation. That is correct. This is para-hydroxybenzaldehyde. Ortho-hydroxybenzaldehyde, and this is para-hydroxybenzaldehyde. This is para-hydroxybenzaldehyde. These two can be separated by steam distillation. Perfect. Because this is steam volatile due to intramolecular hydrogen bonding. Since OH group and CHO group coming at a nearby position, there will be intramolecular hydrogen bonding. So what? The intermolecular attraction decreases. It becomes more volatile. This is more volatile and this is less volatile. This is less volatile because here you have intermolecular hydrogen bonding. So both the molecules have hydrogen bonding. In para-hydroxyphenol, you can see the groups are 1,4 position. There is no intramolecular hydrogen bonding. I'm sure you know the presence of intramolecular hydrogen bonding make the compound more volatile. So this is steam volatile and this is not. And they can be separated by steam distillation. So second statement is correct. First statement is wrong. What is the answer? Option 3 is the correct answer. Option 3 is the correct answer. Okay. Fine. Next question. 61. Given below are two statements for the following reaction sequence. Statement 1, statement 2. Again, the correct, incorrect nature. First statement, the compound Z will give yellow precipitate with NaOI. Statement 2, compound Q has two different types of hydrogen atom, aliphatic, aromatic, in the ratio 1:3. Let's find out compound X, molecular formula C3H6Cl2. 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 Is that matching? C3H6Cl2. This could be compound X. Looking at the reagent also. So it can be 1,2-dichloropropane, 1,1-dichloropropane, 2,2-dichloro. We don't mind. So this treated with the excess, any of the compound. This contain many isomers. It can be 1,2, 1,1, 2,2, 1,3, doesn't matter. It is treated with the excess of NaNH2. We get a compound Y, and the compound Y is, there will be two-step dehydrohalogenation. Hope you remember. Once the chlorine goes and the hydrogen goes, and then this chlorine goes and the hydrogen goes, and the result will be CH3C triple bond CH. This is the compound Y. That is the compound Y. Now, why treated with sulfuric acid and mercuric salt? There will be hydration process. Propine undergoing hydration. Propine undergoing hydration treated with H2SO4 and Hg2 plus. You will get CH3COH according to Markovnikov addition, which will immediately tautomerize. You get a acetone, you get a ketone. This is the compound what? Z. This is the compound Z. Okay. Now, the same molecule Y undergoing treated with the red hot iron tube. Hope you remember the reaction, this one. Cyclic trimerization. Cyclic trimerization. Ethine undergoing cyclic trimerization, we get benzene. While propine undergoing cyclic trimerization, you get mesitylene. It is studied in the class. You see, ethine undergoing cyclic trimerization. Ethine undergoing cyclic trimerization. Hope you remember the reaction. This is ethine undergoing cyclic trimerization. One bond switched here, one bond switched here, one bond switched here when treated with a red hot iron tube. When treated with a red hot iron tube, you will get benzene. Cyclic trimerization of ethine. Similarly, propine undergoing cyclic trimerization. What will be the result? Studied in the class. This is propine molecule number 1. This is propine molecule number 2. And this is propine molecule number 3. It will undergo cyclic trimerization. A bond will be introduced between this carbon like this. A bond will be introduced between this carbon. A bond will be introduced between this carbon, and you get 1,3,5 trimethylbenzene. You get 1,3,5 trimethylbenzene, and that is called mesitylene. Mesitylene, that is the compound. Which one? Q. This is compound Q. Okay. Now on to the statements. Compound Z will give precipitate with NaOI. Correct. Acetone can give you haloform test. Acetone, when treated with NaOI, you get a iodoform reaction. What is the reaction? This when treated with NaOI, iodoform reaction. The reaction will be this methyl group will be converted to iodoform. You get CHI3, yellow precipitate, and this will be converted to the oxidized product CH3COONA. That will be the product. So option 1 is, statement 1 is correct. What about statement 2? Statement 2, Q has two different types of hydrogen atom, aromatic, aliphatic. Two different type of hydrogen atom, aromatic, aliphatic, in the ratio 1:3. So, aromatic, aliphatic hydrogen in the ratio 1:3. Let's verify. Here you have aromatic hydrogen. Here you have aromatic hydrogen. Here you have aromatic hydrogen. So, aromatic hydrogen, it is 3. And aliphatic hydrogen, it is 3. This is aliphatic hydrogen. 3 plus 3 plus 3, 9. So it is 1:3. That is also correct. So statement 2 is also correct. So statement 1 correct, 2 correct. Excellent way, excellent question. Both are true. Both are true. Third statement is the correct answer. Okay. So please have a look at the reaction once again. This is compound X. When treated with NaNH2 excess, you get a propine. Propine hydration, you get acetone. Any higher alkane hydration. Ethine upon hydration, you get a ethanol, aldehyde. Any higher alkane upon hydration, you get corresponding ketone. Propine hydration, you get a propanone, and the propanone, that is acetone, will respond to haloform test. First statement correct. Okay. While the next reaction, propine passing through red hot iron tube, similar to this reaction, there will be cyclic trimerization. You get a 1,3,5 trimethyl benzene, which is so called mesitylene, and the ratio of hydrogen atom aromatic and aliphatic type of hydrogen atom in mesitylene, it is 1:3 ratio. 3:9, 1:3 ratio. There are 3 aromatic hydrogen and there are 9 hydrogen linked to aliphatic system. Hence, that statement also correct. Okay. Is it clear? Fine. Next question. 62. Again, 5 options are given based on 4 isomeric compounds. Based on 4 isomeric compounds, 5 statements are given. Identify correct statement. Identify correct statement. Let's have a look at statement A. QRS will give precipitate with the 2,4-DNP. I'm sure all of you remember 2,4-DNP. 2,4-dinitrophenylhydrazine. 2,4-dinitrophenylhydrazine. This is the molecule H2N NH. This is 2,4-DNP. 2,4-dinitrophenylhydrazine. 2,4-DNP. Right? Reaction of aldehydes and ketones with ammonia and derivatives. We are learning 7 reactions. Reaction with ammonia, reaction with amine, reaction with hydroxylamine, reaction with hydrazine, reaction with phenylhydrazine, reaction with 2,4-dinitrophenylhydrazine, that is 2,4-DNP, which is also called Borchers reagent or Brady's reagent. The product obtained is yellow-red colored precipitate used for the detection, separation, identification, purification of carbonyl compounds. Right? And final one more reaction with the semi-carbazide, giving semi-carbazole. So the statement is QRS will give precipitate with the 2,4-DNP. It gives precipitate with the aldehydes and ketones. What about Q? Q is an aldehyde. Yes, it will give. Q is an aldehyde. Yes, it will give precipitate with the DNP. R is a ketone. Yes. S is a ketone. So this is a true statement. A is a true statement. A is a true statement. Third choice out. What about B? P and Q will give positive Bayer's test. P and Q will give positive Bayer's test. Bayer's test is given by alkenes. Bayer's test is given by alkenes. Hope you remember. Alkenes, when treated with the cold dilute alkaline or aqueous solution of KMNO4, the pink color, purple color gets decolorized by hydroxylation reaction. That is Bayer's test. Bayer's test is given by alkenes. Out of the 4, Bayer test is given by only P. It's given P and Q will give positive Bayer's test. P will, Q will not. So B is wrong. Statement B is wrong. So this is out. Again, we have 2 choices. Now see, Q and R will give sooty flame. Q and R will give sooty flame. Yes, Q is aromatic, R is aromatic, so C is correct. Q and R will give sooty flame. So we get the answer. Option first choice C is not there in option 2. Option first choice ACD. ACE. What about D? R and S will give yellow precipitate with iodine and NaOH. R and S. R and S. R will give. You see, R can give. There is a methyl keto group. R will respond to this reaction. What about yes? Yes will not. Yes will not respond because this is a methyl keto group. R can give this reaction. Yes cannot. So this is a wrong statement. D is a wrong statement. And what about E? Q alone will deposit silver with the tolerance reagent. Q alone will respond with the tolerance test. Yes, that is a true statement. You see here, this is the one and only aldehyde. This is alcohol. This is alcohol, allyl alcohol, ketone. There is one and only aldehyde, and only Q will respond to tolerance test. There is out of the four compounds, only one is aldehyde, and that will give tolerance test. Right? And option E is also correct. ACE is the correct answer. ACE is the correct answer. Okay. Hope you remember tolerance test given by aldehydes. There will be silver mirror test. Aldehydes will be tolerance reagent ammoniacal silver nitrate. An aldehyde, whether aliphatic or aromatic, when treated with ammoniacal silver nitrate, you will get the aldehyde is oxidized to carboxylic acid and silver will be reduced. There will be silver mirror forming on the walls of the test tube. Next question. Question number 63. Let's try Grignard reagent RMGBr. React with water and forms gas Q. 1 gram of Q occupies 1.4 decimeter cube at STP. P on reaction with dry ice in dry ether followed by H3O plus forms a compound Z. 0.1 mole of Z will weigh. Let's try to figure out what is being explained. RMGBr react with water. So RMGBr when treated with water, you know Grignard reagent is highly sensitive to water. It's going to break here plus and minus. This will break here minus and plus. So this R will capture H. You get RH. So this is P, and this is Q, a gas. 1 gram Q occupy 1.4 decimeter cube at STP. So 1 gram occupies 1.4 decimeter cube, that is 1.4 liter at STP. Therefore, how many gram will have 22.4 liters? That you can find out. How many gram? It will be 22.4 liter. That will be molar mass. This will be 1 mole, and that is molar mass. So it is 22.4 divided by 1.4. This is the molar mass of compound Q. That is the molar mass of compound Q. 22.4 by 1.4. That is 224 by 14. You will get 16, isn't it? You will get 16. This is the molar mass of the compound, right? And it's very simple to understand. This is nothing but methane. We are talking about the alkane methane, and we are talking about the P. P is nothing but CH3MgBr, and this CH3 capturing proton, you get a CH3H, that is methane. So from this calculation, we get molar mass to be 16. From that, we get Q is nothing but methane. From that, we can understand the Grignard reagent is CS3MgBr. This is P. Now that P on reaction with the dry ice. This on reaction with the dry ice. Dry ice means solid carbon dioxide. Hope you remember the very popular reaction preparation of carboxylic acid. This is plus, this is minus, and this will attack over here, and you will get CH3 COOMgBr, which upon hydrolysis you get CH3 COOH. That is the compound Z. Idana compound Z. Now what is our question? 0.1 mole of Z will weigh. This is acetic acid. Acetic acid molar mass equal to 60. So 1 mole is 60. Therefore 0.1 mole will be 6. The answer is 6. So from this data, we understand the Grignard reagent is methyl magnesium bromide, and we understand the compound Q is methane. Okay, compound Q is methane. We understand from this calculation, and thereby we understand the Grignard reagent is methyl magnesium bromide. From that we understand the final acid obtained is Z is acetic acid, ethanoic acid. Ethanoic acid molar mass is 60, everybody know. Right? 60 is the molar mass of acetic acid. And what is the question? 0.1 mole of acetic acid. What is the weight? 6 gram. Fine? Yes. Next question. 64. Again, statement based question. 64. First statement. Cross-aldol condensation between two different aldehydes will always produce 4 different products. Wrong. Wrong. 2 different aldehydes always giving 4 different products. Suppose you are taking CH3CHO plus CH3 CH2 CHO, 2 different aldehyde A1, aldehyde A2. You will get 4 products, no doubt. What are the 4 products? Number 1, A1 condenses with A1. Number 1, A1 condenses A1, simple aldol condensation. Number 2, A2 condenses with A2, simple aldol condensation. And number 3, A1 condenses with A2, and number 4, A2 condenses with A1. So you will get 4 products, no doubt. 2 simple aldol condensation and 2 cross aldol condensation. A1 undergoing condensation, A1, A2 undergoing condensation, A2, A1 attack A2, A2 attack A1. You will get 4 products. But not necessarily always. Imagine you are dealing with a benzaldehyde. Imagine you are dealing with a benzaldehyde and ethanol. You don't get 4 products. This can undergo self-condensation. This can attack this. But this cannot undergo self-condensation, or this cannot attack this. Only one cross product will be obtained. Only one cross aldol product will be obtained, and that aldol product will be a condensation over this region, and the condensation product will be CH double bond CH-CHO. This is the one and only aldol product we get by cross aldol condensation, because this only contain alpha hydrogen. Alpha hydrogen is acidic in nature, and that alpha acidic nature of alpha hydrogen trigger aldol reaction. So only here you have alpha hydrogen, and this can form a carbanion and attack this. While here there is no alpha hydrogen. This is alpha carbon. There is no alpha hydrogen. So A aldol reaction cannot be triggered by benzaldehyde. So if you take an aromatic aldehyde like benzaldehyde treated with another aldehyde, you don't get 4 products. You will get only 2 products. What are the 2 products? This undergoes self-condensation, you get 1 product. A base attacking on this hydrogen, you will get a carbanion CH2 minus CHO, and that attacking this carbonyl center, you get 1 product. So only 2 products are obtained. So that statement is not universally correct. Suppose you take an aldehyde like this, that statement is correct, but not always. So cross-aldol condensation between 2 different aldehydes will always produce 4 different products. It is wrong. Even cross-aldol condensation, here you get only 2 products. If we are talking about cross-aldol products only, it is only 2 products, not 4 products. Okay. Number 2, and here only 1 product, here only 1. So according to the nature of aldehydes that involved in the reaction, cross-aldol products may vary. Statement number 2. When semi-carbazide react with a mixture of benzaldehyde and acetophenone under optimum pH, it forms a condensation product with acetophenone only. This is benzaldehyde and this is acetophenone. A semi-carbazide react only with acetophenone. Wrong. A semi-carbazide can react with benzaldehyde as well as acetophenone. Both are carbonyl system. This contain a carbonyl system. This is benzaldehyde containing a carbonyl compound. This is acetophenone. This is acetophenone. There is a carbonyl system. When there is a carbonyl system, whether it is benzaldehyde or acetophenone, it will react with a semi-carbazide. Hope you remember what is semi-carbazide. This is the reaction with the semi-carbazide. This is semi-carbazide. There will be a condensation over here and the product obtained will be C double bond N NH CONH2. This is called semi-carbazone. So whether benzaldehyde or acetophenone, both will react with semi-carbazide and you get a semi-carbazone. So this is also a wrong statement. Both are wrong statement. Which option? Option 3. Option 3 is the correct answer. Okay? Yes. Next question. Yes. Question number 65. Consider the following 2 reactions A and B. Numerical value of molar mass of X plus molar mass of Y is. Please analyze the reaction. Phenol with the metallic sodium. Phenol with the metallic sodium. The product obtained will be sodium phenoxide. Sodium phenoxide and hydrogen gas. This is X. Now, what about the second reaction? Carboxylic acid with the NaHCO3. You will get sodium carboxylate COONA plus H2O plus CO2. This is the gas. This is the gas Y. So gas X is hydrogen, gas Y is carbon dioxide. Sum of molar mass, numerical value, molar mass of X and Y. This molar mass is 2, this molar mass is 44 and the answer is 46, the third choice. Correct answer. Okay, one is phenol. Phenol with NaOH. Sorry, phenol with even NaOH. No, with the metallic sodium. Phenol with the metallic sodium, hydrogen gas is liberated. while the second one is benzoic acid. Benzoic acid with the sodium bicarbonate, you get brisk effervescence escaping carbon dioxide gas. And sum of molar mass of the two gases. Very simple question. Okay. Next. 66. A student is given one compound among the following that gives positive test with the tolerance reagent. Out of ABCD, which will give positive test with the tolerance reagent. That means the one which will give you aldehyde. The one which will give you aldehyde. That is the question. Let's have a look at this one. This upon hydrolysis, you will get, suppose it is hydrolyzing over here, you will get OH, OCH3, OH. This is what you are getting. Right? And that is not giving you tolerance test upon hydrolysis. Here also you don't get any aldehyde. Option C should be the correct answer. Because as you can see, upon hydrolysis, this molecule will open up. And you have one OH group here. And here already one OH group. Here there will be one OH group. And this will turn aldehyde group. That will turn aldehyde group. Because two OH group on one carbon, it is unstable, it will be converted to aldehyde group, and this aldehyde group. So this part of the molecule, the way you check the glycosidic linkage breaking in a sugar molecule, giving a non-reducing sugar. I'm sure you know how you check the non-reducing nature of sucrose, how you check the reducing nature of lactose, maltose, etc. That functional group will open up and you will get the CHO group. That is the point. So this area will open up and you will get a CHO group, and that will reduce the tolerance reagent. So this CHO group will be reducing tolerance reagent, and you get silver mirror test. Many times discussed tolerance test. Tolerance reagent is ammoniacal silver nitrate, a mild oxidizing agent. It can oxidize both aliphatic and aromatic aldehydes converted to carboxylic acid, and itself it is getting reduced to silver mirror. So RCHO, when treated with the tolerance reagent, that is ammoniacal solution of silver nitrate, you will get RCHO. This is basic medium, RCOO minus, and you will get silver mirror precipitated. On the walls of the test tube, silver will be deposited and you get a mirrory appearance, silver mirror test. It is given by both aliphatic and aromatic aldehydes. Remember, Fehling solution will give you a test for only aliphatic aldehyde, not aromatic. Okay. So, if the compound is option C, third choice is the correct answer. What about D? These are not able to give any sort of aldehydes. This also. So, it's option C, the correct answer. Okay. Next. 67. Which is true about haloform. True about haloform reaction. 5 statements are given. True about haloform reaction. Option A. Sodium hypochlorite react with Ki to give KOI. Sodium hypochlorite react with Ki to give KOI. That's a true statement. Sodium hypochlorite NaOI plus Ki giving KOI. It's a true statement. KOI is a reducing agent. Wrong. KOI is an oxidizing agent. Hypoiodite, hypochlorite, they are oxidizing agents. So statement 1 correct, 2 wrong. I mean A correct, B wrong. Alpha beta unsaturated methyl ketone will give iodoform reaction. Yes, they can give iodoform reaction. This is a methyl ketone. This is alpha carbon, beta carbon. Alpha beta unsaturated compound. You will get a iodoform reaction. What will be the result? What will be the result? This part of the molecule will be converted to this, and this methyl group will be converted to CHX3 haloform. In fact, what is the point of methyl keto group? Commenting methyl keto group give haloform test. That methyl part is converted to haloform. Okay. And what about the remaining part? The remaining part is converted to oxidation product. One important point you can see here, in that statement as well as in this example, the unsaturation remain intact. During haloform reaction, the unsaturation part remain intact. Nothing happens. So C is correct. C is correct. So A correct, B wrong, C correct, A correct, B wrong, C correct. D. Isopropyl alcohol will not give iodoform test. Wrong. This is isopropyl alcohol. Isopropyl alcohol having methyl carbinol group. It will give iodoform test. D is wrong. D is wrong. No use. Methanoic acid will give positive iodoform test. Methanoic acid will not give positive iodoform test. HCOOH. Not only methanoic acid, an acid group is not responsible giving a haloform test, because haloform test is nothing but oxidation reaction. An acid is oxidized version of a compound. An acid means it is an oxidized product. How can an acid be oxidized further? So that is not possible. So methanoic acid will give positive iodoform test. That is wrong. So the answer is option A and C. Answer is option A and C. That is the answer. Right? Fine. Next. Question number 68. Again, some statement based question. എന്താ വേണ്ട? Choose the correct answer from the iodoform. Oh, iodoform test can differentiate between. Iodoform test can differentiate between. What about A? Methanol, ethanol. Methanol, ethanol. Correct. Methanol will not react. Ethanol will react. This is methanol. It is unfit giving iodoform test. This is ethanol. This is ethanol. That will give iodoform test. Methanol does not contain meth. It is carbinol. We want methyl carbinol. We want a methyl carbinol group. So ethanol can give iodoform test. Methanol cannot. Now option B. Acetic acid, propanoic acid. No, both will not react. Option A. This is statement A. Statement A is possible. Statement B, both are not possible. This is not possible. This is not possible. To differentiate means one should react, one should not. So B is out. C. Cyclohexene, cyclohexanon. Cyclohexene, cyclohexanon. No, both cannot. C is out. C is out. Cyclohexene, cyclohexanon. Both will not respond to iodoform test because it is unfit to performing iodoform test. To perform iodoform test, we need to have a methyl keto group or methyl carbinol group. We need to have a methyl keto group or methyl carbinol group. This can give you iodoform test. Both are absent here. Now option D, diethyl ether and pentan 3 on. Diethyl ether and pentan 3 on. Diethyl ether, this is diethyl ether and pentan 3 on. This is pentan 3 on. This does not contain methyl keto group. This is ethyl keto group. So this will not. D is out. Anisole acetone. Anisole means OCH3. Methoxybenzene. That is anisole. Will not give iodoform test. And acetone will. This is acetone. Acetone will give. So E can. So option A and E. Option A and E. Fourth choice is the correct answer. Option A il methanol, ethanol. Ethanol can, methanol cannot. Option E il anisole. Anisole and acetone. Anisole not, acetone yes. Acetone will give you iodoform test. Anisole will not. Now in option B, statement B, both cannot. This is not the test for carboxylic acid. Both cannot. To distinguish, as I said earlier, to distinguish A and B, to differentiate A and B using a test, A should give a test, B should not, or vice versa. One should give the test, one should not. Then only we can differentiate. Okay? In B, C, D, both does not give, both the out of the pair, both compound does not give iodoform test. Okay? Fine.